So I'm explaining assignment 5, and I'm going to explain the functions that I was assigned to implement. So the print leaves function here, so what a leaf is, on the left-hand side, I made a diagram of the tree that I'm implementing in the driver program. So the leaves here are the nodes without children. So how the algorithm works, how it goes, is that it takes so it's recursive, so it takes in a node and then its root in this case. So it takes in the node and it says if get left is null, which means if it's nothing and the right node equals null, then you print it out. However, and then you go again. So, however, if you do have a child, then you simply get skipped over, and if you don't have a child, the information gets printed. So how it would work here, 50, it has two children, so no, it won't get printed, and then it recurs to 25. It has children, so it goes to 8. 8 has no children, so it gets printed, and the recursion stops there for 8. And then it goes back to 25. Then um, 31 has no children, so it gets printed. 75 has children. 60 has no children, it gets printed. 81 has no children, it gets printed. So the interior nodes, they're the opposite of leaves. Interior nodes are parent nodes or nodes that have children. So the algorithm here, it just simply checks if on either side or if they have a child at all. So if no dot get left is not a null value, then that means it has a child. And what it does, it's a counter, it's a counter function. So you return one. So 50 has two children, so you just return one plus recursive counter. Then it goes to 25. 25 has children, so that's one in the counter. 8 has no children. 31 has no children. No iterating going on here. And then 75 has children, so then the counter goes up one. And then the leaves have no children. So then the expected value is 3. So get root successor. The successor node is the leftmost node on the right subtree. So in this case, it'd be 60. So what it does is that it checks if the current node, the root node in this case, has a right hand child, and it does in this case. And then when it does, it iterates or it recursively goes to get the leftmost node, and in this case, it's 60. So is full binary tree. So this checks if every node has 0 or 2 children. If a node has one child in the tree at all, then it is not a full binary tree. So the algorithm here, it's recursive once again, and so it checks if either, it checks if only one node has something. So this return false gets triggered by um by a node only having one child in particular. And then if not, it returns or goes recursively. So 50, 25, 25 has two children, 8 has 0, 31 has 0, and 50 already has two children, 75 has two children, 60 0, 81 0. So it returns true. So the is balanced function, so balance in a tree sense, it compares the length of the left and right subtree, and if the difference exceeds 2 in either direction. So if the absolute value of the difference of the sides exceeds 2, then it is not balanced. So this one is balanced, obviously, and I'll go over the exact algorithm here. So so initially, so the first thing it asks for is the left height. So what's the left height for 50? So left height for 50, it calls the function once again. So then now we're concerned, what's the left for 25? And then we call the left on 8, and we can get a tangible answer this time, which is 0, because if you get left of 8, then the node equals null and it returns 0. And on the 8 node 2, we also have to find out what the right is, and the right is 0. Also because, the right returns 0. So so in order to get back to 25 here, we have to return a value. And so this conditional right here, it checks if the absolute value of height of the difference of heights exceeds 2. In this case, 0 minus 0 is 0. So we don't have to return -1. We don't have to say it's not balanced. So now we can return this. So math.max, left height, right height. So you take the bigger number of the two and then you add 1. So in this case, it's 1 because 0 is 0. Now we want to get the right-hand side of 25. So we have to get the left-hand side of 30, 31, which is 0, and then the right-hand side, 0, and then we return the max of that plus 1. So then right is 1. So then now we take the bigger number of 25 here, which 1 either way goes, and then we add 1. So then 2. So left hand is 2. This checks out because 1, 2, the length of the left subtree is 2. Now we want to get the right hand of the root. So then we try to get the left hand 75 first, and then we need to get the left hand of 60, which is 0. The right hand is 60, 0. And then you take the bigger one, add 1, so the left is 1. Then we got to get the right. Then the left of 81, 0. Right of 81, 0. And we add 1 recursively. And then the bigger 1 plus 1, 2. So then the absolute value function here, just to make sure it isn't exceeding anything, we take the absolute value of 2 minus 2, 2 minus 2, and it is 0, and it is smaller than 1, so we're in the clear, and then we add 1 to that. So we return 1 to the function, and the public function is balanced, checks if the root is -1. If it's -1, it's false. And in this case, it's +1, so it is a balanced root, or it is a balanced tree in general. So this is the second test case here. I won't go over it in like the exact detail. Actually, wait. I need to summarize the findings here. So test case 1, the leaf nodes 8, 31, 60, and 81, and the number of interior nodes 1, 2, 3. The root successor is 60. It is a full binary tree and it is balanced. So these corroborate the correctness of the algorithm. Now, test case, so I'm doing another test case here with letters. The same logic follows. Um, the characters are sorted by their ASCII values, so we could experiment with other data types here, and we just have to go quick through these. So the leaf nodes, B, P, and Z, it's on here, yep. The number of interior nodes, 1, 2, 3, and 4. They have children, yes. The root successor is P, and it is not a full binary tree as C and Y only have one child, and it is balanced because the length, the left subtree length is 2, and the right subtree length is 3, and the absolute value of those two is 1, and that is less than 2. So that is a balanced tree. So this tree is of note as it is a skewed tree. It's a special exception in a lot of tree problems. So it's an edge case, and it's useful to test the functionality of the program. So we would expect here the leaf node is 10, and then the number of interior nodes is 4, 1, 2, 3, 4, and then the root has no successor as there is no right subtree, and it is not a full binary tree, and it is very much not balanced. So yeah, that is assignment 5.